because a delivery tube have a small surface area, that will cause the hydrogen produced to be less than the rate at which it is being dissolved. What I mean, the rate at which hydrogen chloride is dissolved in water is faster than the rate at which it is being produced. And consequently, there is a decrease in atmospheric pressure within the container from which is being generated. And this causes the atmospheric pressure to push the water up the delivery tube. And that is what we call sucking back. That's what we call sucking back. But if you use inverted funnel provides a large surface area in such a way that water becomes difficult, or it becomes difficult for water to undergo process of sucking back, since we cannot have water floating. So, but ask, what happens when hydrogen chloride is dissolved in polar solvent and when it is dissolved in non-polar solvent? We said that pure hydrogen chloride is covalent compound, meaning it dissolves in non-polar solvents, such as benzene, such as methylbenzene, such as tetrachlorobenzene, and so on. Even it can dissolve in ethanol. Ethanol is a non-polar solvent. But what happens when you dissolve it in water and when you dissolve in non-polar solvents? We have found out that when you dissolve it in water, the hydrogen chloride dissolves in water, and water enhances its ionization by forming hydrogen ions plus chloride ions. And this one makes it an acidic solution. And when it makes it an acidic solution, it becomes what we call hydrochloric acid. This is called the hydrochloric acid, which we should say when they ask an aqueous solution of hydrogen chloride is referred to as hydrochloric acid. So now it is on that note that we look at the properties of hydrogen chloride gas in aqueous solution and in non-polar solvent. What happens now? Hydrochloric acid, like any other acid, aqueous, turns blue litmus paper red. It turns blue litmus paper red and reacts with both bases, carbonates, and metals. These metals must be higher in the activity series. They must be above hydrogen. Now, with bases, we mean either oxide or hydroxide. For example, when we look at with bases, we can take an example of like copper 2 oxide. What happens when hydrochloric acid is added to copper 2 oxide? Remember last time I said copper, when you add a liquid to solid, and the solid disappears, we don't use the word disappear. It must have, something must have happened, a process, and that process is dissolving. So when you add copper to oxide and you add it to hydrochloric acid, we said when we are studying alkalis and acids, we said a base reacts with acid to form salt and water. And in this case, the salt is copper 2 chloride. Copper 2 chloride plus water. And when you write equation, you mind about balancing the equation. When you want to balance the equation, now you look at this chloride and put here 2. That is the reaction between a base and acid. Or oxide. When we have sodium oxide, we form sodium chloride. When we have magnesium oxide, we form magnesium chloride. When we have zinc oxide, we form zinc chloride. When we have aluminum oxide, we form aluminum chloride. When we have zinc oxide, we form zinc chloride. So there is no need of writing as many equations on the same. What you need to know is the oxides produces corresponding chloride. So this equation is enough. You should know that the base in form of oxide reacts with acid and produces the corresponding chloride. And now, the observation now, you need to know the color of the oxide. The observation differ because each oxide has its own color. Like copper oxide, we know it is black powder. So we say black powder dissolves to form what? You should know the color of copper 2 ions. It is blue, to form blue solution. To form blue solution. By the way, I want you to note that at this level, I'm talking about at this level. Don't push me where I cannot reach at this moment. At this level. Most of salts we are supposed to study, that is from sodium up to silver, the salts are colorless. The salts form a colorless solution, except copper 2 ions, which forms blue solution, iron 2 ions, which form green solution, and the iron 3 ions, which form brown solution. The rest, magnesium ions, sodium ions, potassium ions, zinc ions, aluminium ions, silver ions, red 2 ions, all are colorless in solution and white in solid form. But these ones, the copper 2 ions, iron 2 ions, iron 3 ions, they are brown. This one is blue, copper 2 ions, iron 2 ions is green, and iron 3 ions is brown. The rest are colorless. So that's why it is on this note that we say a black powder dissolves to form a blue solution. If it was zinc oxide, we would have said zinc powder which is white. The white powder dissolves to form a colorless solution. Magnesium and so on. Even all oxides, most common oxides at this level are white in color, except red 2 oxide, which is reddish black, which is yellow at room temperature. But the rest of metallic oxides are white in color. No more metallic oxide are white in color. Once again, apart from copper oxide, which is black, and the others. But the rest are white in color. The rest which I have mentioned, which form colorless solution, are white in color, except red 2 oxide, in addition to these ones. So learn how to state your observations and how to write equation. Now, you meet me when I don't know how to write the formula of copper 2 oxide. But I know that when I react a base, which is oxide, plus acid, from now, you should add to what you know and remember that writing an acid, when you write hydrogen ion, is enough to mean that you have written an acid. I don't need to see the name unless I have asked to write the formula. But when I say a base reacts with acid, in this case, we mean that hydrogen chloride is also part of an acid and the family of acid. It forms water. So I put here too. This is the equation which you can use to write the reaction between the base. Or people can say copper 2 oxide. Those who say the solid does not ionize, then plus acid, you form what? You form copper 2 ion plus water. But you can see in most cases when you're writing an equation, this one becomes even somehow difficult to write because you might forget this one. This one is correct. I have seen the argument where people say solids do not ionize, but that is not correct. So do not ionize when in water because they are not insoluble in water. They remain the way they are. But this is the acid. Whereas copper 2 oxide is insoluble in water, it is soluble in acid. Therefore, in acid it does ionize. So don't be misled on that. People who, sometimes we say, insoluble solid do not ionize. That is wrong. Even when electric current is passed through insoluble solid, it does ionize. So this oxide does not ionize in solid form, but when you add acid, it ionizes to form water. Otherwise, if it does not ionize, then how does it react? So this equation, oxide and hydrogen, even if I don't know, even if I wake up and say, we are at UBC, even if we say UBC oxide reacts with another TV acid, what do you get? Do you know the formula of UBC? No. You simply say, I know the formula of oxide, and I know the formula of hydrogen ions, which is acid, and you form water. Ignore the others because they are not part of the chemistry. So in the same way, these ions like copper and chloride are not part of the chemistry. They do not undergo chemical reaction because they form a compound which ionizes to produce the same ions from which it was formed. So don't look at that one. Then we have also hydroxide. You can pick any hydroxide you want. Which hydroxide can we pick? Maybe we pick what? Sodium hydroxide. Sodium hydroxide will react with hydrochloric acid. What do you get? You get sodium chloride plus water. It is also base, so it forms salt and water. In a similar way, we can ignore that we don't know sodium. In a similar way, we can say we don't know the formula of sodium. So we write hydroxide, and the charge is this one, plus the acid, and you get what? Water. And this one is called ionic what? Ionic equation. This is called ionic equation. And in any case, the only equation which takes place in any chemical reaction is an equation. This one is not an equation, it's a molecular equation. Because sodium chloride, sodium ions, and chloride ions does not participate in chemical reaction. It represents just what is taking place. But this one, it is exact, it involves only species that are taking place in chemical reaction. Tomorrow they might wake up and say, what, do you know like tartaric acid, tartaric base, plus uranium acid. God forbid they might not be there, but I'm giving as an example. Do you know the formula? And I'm asking you to write the equation. So if they talk of a base or hydroxide, just ignore this one because you don't even know it. You write hydroxide. You don't know uranium acid. So you write hydrogen ions, and the product is water. You are not different from someone who struggles to get the formula of this compound, yet they do not take part in chemical reaction. So like any other acid, hydrochloric acid reacts with sodium hydroxide to form salt and water. Any other hydroxide, it can be potassium hydroxide, it can be magnesium hydroxide, it can be zinc hydroxide, aluminum hydroxide, and so on. So that one shouldn't be a problem. What you need is to know that you produce salt and water, and the major product is water. Then, like any other acid, it reacts with carbonate. Which carbonate do we pick? I think preferably we pick calcium carbonate. Because calcium carbonate, so far we mainly use it. When you react, you add hydrochloric acid, you get calcium chloride, carbon dioxide, and water. So what does it mean? In general, any carbonate, you just pick it anywhere where you come across it, any carbonate, and you react it with any acid. In this case, we are taking hydrochloric acid. You get salt, carbon dioxide, and water, no any other product. You get you get salt, carbon dioxide, and water, or any other product. But you must balance the equation. So in this case, because we are using calcium carbonate, we are getting calcium chloride, carbon dioxide, and water. Suppose we use sodium carbonate, we get sodium chloride, carbon dioxide, and water. Suppose we use aluminum carbonate does not exist at room temperature. Suppose we use zinc carbonate, we get zinc chloride, carbon dioxide, and water. And you can see the common product in any of this reaction is carbon dioxide and water. Therefore, don't haggle to get the answer. Simply say the carbonate, whether it is sodium, whether it is calcium, whether it is what, reacts with acid to form carbon dioxide and water. To form carbon dioxide and water. That will generalize all the equation. Because we know calcium carbonate produces carbon dioxide and water. But any carbonate, so I do not need to know even the formula of carbonate I'm using. But the moment I hear of a carbonate, I will know that any carbonate will react with hydrogen ions, which is acid, to form carbon dioxide and water. Tomorrow I can bring even sulfuric acid, the equation remains the same. Even if you put nitric acid, the equation remains the same. So please don't condense all your work so that you can read little but understand more. So, what do you observe? Suppose, because you are supposed to tell us if you are carrying out an experiment concerning a carbonate and the acid, what you observe mainly is this one, all carbonates in solid form are white. Once again, except copper 2 carbonate, which is green. Except copper 2 carbonate, which is green. The rest are white in color. I'm not talking of transition metals. I'm talking of carbonates which we study at this level, at ordinary level. Those other carbonates, you will meet them later. But at the moment, the most of the carbonates we use in lab at this level, they are white in color. So which means, and they are powder in form except sodium carbonate crystals. The rest of carbonates are anhydrous. So this white powder dissolves in the acid. And in this case, there must be something happening because of production of gas. There is effervescence or bubbles of colorless gas. So the white powder dissolves with effervescence of colorless gas to form a colorless solution. We said most metal ions form a colorless solution, except copper, iron, and iron 3, iron 2 and iron 3. So that is the observation. Whether you use sodium carbonate, whether you use zinc carbonate, whether you use lead 2 carbonate, all of these will dissolve with effervescence of colorless gas to form a colorless solution. Because they are white. Unless I use copper. Unless I use copper 2 carbonate, but the equation remains what? The same. It is only observation which changes. In this case, the green powder will dissolve with effervescence of colorless gas to form a blue solution, a light blue solution for this case. So carbonates are the same. Then with metals, we mean metals above hydrogen in the reactivity series. For instance, copper does not react with dilute hydrochloric acid. Copper does not react with dilute hydrochloric acid because it is below hydrogen in the reactivity series. Therefore, it cannot displace it. In this case, we need metals above hydrogen in the reactivity series. We need metals above hydrogen in the reactivity series. And this one include, we can use like magnesium or zinc. We can use zinc plus hydrogen. What do we get? Hydrogen chloride, we get zinc chloride plus hydrogen. We get zinc chloride plus hydrogen. So what do we include? We put 2 here. What does it mean? It means all metals above hydrogen in activity series All metals above hydrogen in reactivity series, all metals above hydrogen in activity series reacts with dilute acids. Reacts with dilute acids to form zinc chloride, to form chloride and hydrogen. In other words, to form corresponding salt and hydrogen. Now, in all of these things, we need to look at conditions. For hydrogen chloride to behave as an acid, it must be dilute. It must be dilute. That is a condition. In order to react with the base, in order to react with carbonate, with the metal, it must be dilute. Then, with the carbonate and the metal, it must be at room temperature. But with oxide, you must provide some heat. With oxide, the reaction is not fast. The reaction between hydrochloric acid and any oxide is faster when the mixture is warmed. But with carbonate and with metal, the reaction with metal, it is even exothermic. Therefore, it proceeds at room temperature and in a fast rate. So, those are the reactions in which hydrochloric acid or hydrogen chloride is acting as an acid. Is acting as an acid. Now, what about when it is dissolved in, what about when it is dissolved in methylbenzene or non-polar solvent? In non-polar solvent. Because sometimes we can have two solutions. One is hydrogen chloride in methylbenzene. Hydrogen chloride in methylbenzene or in non-polar solvent, and hydrogen chloride in aqueous solution. The properties are different. Why? Because here the hydrogen chloride dissolves in water to form hydrogen ions and chloride ions. And it is due to this reaction that hydrogen chloride in aqueous solution behaves like acid or behaves like an ionic compound. So which means it conducts what? The solution conducts electric current. But this one does not conduct electric current. If you do that one in your laboratory, it is just simple experiment. It is simple experiment. Even if you approach lab technician, you would be able to carry out this experiment. And you compare the two. This one reacts with carbonate, reacts with oxide, reacts with hydroxide, and reacts with metals above hydrogen in reactivity series. But this one does not react. It does not react. Whereas aqueous solution reacts with all carbonates, apart from lead 2 carbonate and silver carbonate. That's where the reaction is very slow. Then it reacts with all oxides, and it reacts with all hydroxides, and it reacts with all metals above hydrogen in the reactivity series. All metals above hydrogen in the reactivity series. But in this case, there is no reaction. Leave alone no observable change, but there is no reaction. Meaning there is no observable change. If you mix this one, if you add silver nitrate here on aqueous, the silver ions react with chloride ions to form silver chloride, which is formed as white precipitate. And by the way, that is confirmatory test of hydrogen chloride when using silver nitrate. though we have used concentrated ammonia. But you can also, a gas when bubbled, when hydrogen chloride gas is bubbled through silver nitrate solution, it forms white precipitate. And that gas is considered to be hydrogen chloride, a colorless gas, when bubbled through a solution of silver nitrate and forms a white precipitate, that is hydrogen chloride gas. Even lead 2 nitrate, the lead 2 ions solution, there must be solution. The lead 2 ions react with chloride ions formed from the ionization of hydrochloric acid to form what? To form lead 2 chloride, which is soluble. To form lead 2 chloride, which is soluble. To form lead 2 chloride, which is soluble. So, which is insoluble. To form lead 2 chloride, which is insoluble. But in these two, there is no reaction, or formation of white precipitate. There is no reaction or formation of white precipitate. Why? Because it does not. There is no chloride ions. There is no chloride ions. There is no chloride ions. So you can see the effect of a solvent on the chemical properties of hydrogen chloride. In aqueous solution, the reaction takes place, but in methylbenzene, it does not. Now, the question I want to ask is, why? Why do you think in methylbenzene there is no reaction? Why do you think in methylbenzene there is no reaction? Whereas in aqueous solution, there is a reaction. The answer is simple, and we have talked about it. We have talked about it. We said in aqueous, I repeat, this is almost the third time, in aqueous solution, the hydrogen chloride, the water ionizes, enhances the ionization of hydrogen chloride to form hydrogen ions and chloride ions. It is this hydrogen ions that combines with oxide, hydroxide, or carbonate. And it is this chloride that combines with silver nitrate and lead 2 nitrate. It is these ions that carry electric current. And this is because water is a polar solvent. Water is a polar solvent. But in methylbenzene, I want you to pay attention to this. In methylbenzene, the solvent is non-polar. That means it does not have ions to attract the other one. It's non-polar, and therefore hydrogen chloride, which is also covalent, dissolves in it, but remains in molecular form. It remains in molecular form. It does not form ions. It remains the way it is. So it does not form ions to conduct electric current, does not form ions to react with bases, does not form ions to react with carbonate, does not form ions to react with metals, and so on. It remains as hydrogen chloride, but dissolves because all non-polar solvents dissolves covalent compounds. All non-polar solvents dissolves covalent compound. And when chloride dry, being a covalent, it will dissolve in methylbenzene, but will not ionize. Therefore, it does not react. It does not react. It only reacts like metals when heated. For instance, look at this one. Let me ask this question. When ammonia was bubbled through aqueous solution of hydrogen chloride. Was bubbled through aqueous solution of hydrogen chloride. There was no observable change, but forms white precipitate with solution of hydrogen chloride in methyl benzene. So we are saying when you get ammonia gas and you bubble the ammonia through a solution containing aqueous solution of hydrogen chloride, bubbles through aqueous solution of hydrogen chloride, there was no observable change. Oh, there is no observable change even if you do it now. But when you try to bubble ammonia through a solution containing hydrogen chloride and methyl benzene, you will immediately form a white precipitate. Now, what could be the answer now? What could be the answer? Look at this. We are saying in aqueous hydrogen chloride, the ammonia will react with hydrogen chloride to form. We react with hydrogen chloride in aqueous form. Ammonia reacts with hydrochloric acid to form ammonium chloride, which is very soluble and ionizes to form ammonium ions and chloride ions. And in this case, there is no observable change because the salt formed is soluble. Once the salt formed is soluble, there is no observable change. You can only see a precipitate if the salt formed is insoluble. But in methyl benzene, the hydrogen chloride remains in molecular form. And therefore reacts with ammonia gas to form ammonium chloride. Which is formed as white solid. And since, full stop, ammonia chloride is ionic compound, and therefore insoluble in methyl benzene, which is non-polar solvent. So that's why we are looking at effect of solvent on hydrogen chloride. In aqueous solution, hydrogen chloride is able to ionize. The water enhances ionization of hydrogen chloride forming hydrochloric acid. And because of the formation of ions, it reacts in the same way as hydrochloric acid. But in methyl benzene, it is a non-polar solvent. Non-polar dissolves in non-polar, but because they are all non-polar, they do not ionize. And that's why when you have hydrogen chloride in methylbenzene, you are just keeping it. You are keeping it there. Anytime you want, you can get it as hydrogen chloride. Anytime you want it, you can get it as hydrogen chloride. Not any other compound. Not any other compound. So, it will react like any gas, like the way it is, and to react with ammonia to form ammonium chloride, which is a white solid. And since ammonium chloride is the only compound, cannot dissolve in methylbenzene. And that's why it shall form a white precipitate. So that is the general effect of solvent on on hydrochloric acid, on hydrogen chloride. Otherwise, in aqueous acid reacts the way an acid reacts. So that is about the effect of solvent on the chemical properties of hydrogen chloride. On chemical properties of hydrogen chloride. There are other reactions. We have seen reaction with metals and so on. So, earlier, we saw when we were looking at chlorine, we found out that other reactions of hydrogen chloride, it includes a reducing action. And we found out that it reacts with potassium manganate. Potassium manganate to form potassium chloride, manganese 2 chloride, water, and chlorine. And for those who have, we said balancing, again, you look at the odd. And we thought this one is even, this one is even, so this one cannot, we put 2. And we have affect potassium, we put 2. We affect manganese and oxygen, we put, manganese is 2, we put 2 here. And oxygen, we put 8. And within this, we affected the hydrogen, which is 16. And this case, we affected chlorine, which is 16. But we said we cannot tamper with this one and this one, which makes gives us what? 6. So remain with 10. And that's why we put what? 5 here. Then it also reduces manganese 4 oxide. Still 2, it is a gas. When heated, still 2, manganese, there is, all of these are solids. No, there is water, it's okay. Manganese chloride, manganese 2 chloride, plus chlorine, plus water. Plus water. And in this case, we put 4 there. Plus water. Those are other reactions of hydrogen chloride. Oxidation, it is a reduction reaction. It is a reduction reaction. So in general, we looked at hydrogen chloride. Hydrogen chloride as anhydride of chlorine. And we looked at it, its source is sodium chloride because that's where we get chlorine. And it is formed when a less volatile acid, which is sulfuric acid, in concentrated form, displaces hydrogen chloride from its salt, that is sodium. And we looked at the product is sodium hydrogen sulfate or hydrogen sulfate in general, because the heat produced is not enough to decompose it completely. And we looked at manufacture. It is manufactured from chlorine and hydrogen. The source of chlorine is electrolysis of sodium chloride or brine in concentrated form using either there are 3 different ways in which you can be extracted. One, electrolysis of molten sodium chloride, or electrolysis of brine using mercury cathode, or electrolysis of sodium chloride using titanium as the anode and nickel as the cathode. Any of these 3 can give you chlorine on large scale. Then we looked at the reaction of hydrogen chloride, especially with heated metals. Those metals which are above hydrogen, those metals which are above hydrogen in the reactivity series, they displace hydrogen from their metal when heated. And we looked at iron 2 chloride, formation of iron 2 chloride. Since it cannot be formed with chlorine, then with iron chloride, which is less oxidizing, can be formed. Then we looked at when you dissolve it in water, it forms hydrochloric acid. Therefore, aqueous solution of hydrochloric acid is aqueous solution of iron chloride is hydrochloric acid. And we looked at the effect of hydrochloric acid on carbonates, metals above in activity series, then oxides, and so on. And we looked at the effect of solvent on hydrogen chloride. And we repeated these oxidizing agents. So that is in brief the chemistry of hydrogen chloride. That is in brief chemistry of hydrogen chloride. And we looked, it does not support burning. It does not support burning. And we said fumes in most air, not because it is, but it dissolves in water. So, members of the class, once again, I will welcome you to UBC, our preferred network, and your public broadcaster. I remain Melaman Stanislas, and my number is 077 244 2500. And a teacher of Mount St. Mary's Namagonga, and a born of Mother Kevina, the founder of most successful schools in Uganda. Thank you. Eh? Oh.